Mars, our crimson neighbor in the vast cosmic ocean, has long captivated our imagination. We have sent our robotic emissaries to its rusty plains. We have sent our robotic emissaries to its towering canyons, meticulously searching for any sign that life once stirred upon its surface. For decades, the story seemed to be one of a world that lost its warmth, its water, and its chance at life. But the narrative is changing. New evidence gathered by our intrepid rovers, new evidence gathered by our vigilant orbiters, suggests that Mars is not as static or lifeless as it appears. It hints at a world with dynamic processes still at play. Processes that could either preserve the secrets of a past biosphere, or perhaps sustain a hidden one today. This is not a story of little green men. It is a tale of microbes. It is a tale of chemistry. It is a tale of enduring hope, told by the planet itself. The search for life beyond Earth is one of the most profound quests humanity has ever undertaken. The first major clue comes from an element we often take for granted: the wind. For a long time, we thought the thin Martian atmosphere could only muster feeble breezes. But recent data, particularly from NASA's InSight lander and Perseverance rover, has revealed a different story. The winds on Mars are far stronger and more dynamic than our models predicted. Gusts can whip across the plains with enough force to lift significant amounts of sand and dust, creating vast storms that can blanket the entire planet. These winds are a powerful geological force, constantly sculpting and reshaping the Martian surface, eroding rock, and moving sediment on a grand scale. This is not a quiet, still world. It is a world of atmospheric energy and constant motion. This discovery has profound implications for the search for life. On one hand, these powerful winds could be destructive. If any simple life forms ever existed on or near the surface, aeolian erosion could have scoured away the evidence over millions of years, breaking down delicate biosignatures, scattering them to the four corners of the planet. However, the wind's power is a double-edged sword. While it can destroy evidence, it can also reveal it. By stripping away younger layers, the wind can expose ancient bedrock. Missions like the Mars Reconnaissance Orbiter can map these wind-scoured zones, identifying promising locations for future rovers to investigate. Our second clue lies locked away in the cold Martian subsurface: water ice. We have known Mars has polar ice caps, but instruments like SHARED on the Mars Reconnaissance Orbiter revealed vast sheets of buried ice at lower latitudes. Not just small pockets, extensive layers, sometimes hundreds of feet thick, a massive reservoir of frozen water. A relic of a past climate, a frozen record when water flowed more freely. A planetary time capsule waiting to be opened. On Earth, ice is an extraordinary preservative. Scientists have discovered ancient bacteria, viruses, complex organic molecules, preserved for hundreds of thousands of years. Ice slows chemical decay to a near standstill, protecting delicate structures from degradation. If life existed on Mars, chemical or fossilized remnants could be trapped in subterranean ice. Finding and analyzing this ice would be like finding a library of Martian history, each layer holding the story of its era. Buried ice deposits are more accessible than polar caps and are located in regions that may have been habitable. A future mission could land, drill down just a few feet, and retrieve a core sample of this ancient ice. Such a sample, if returned to Earth or analyzed by a sophisticated onboard laboratory, could be examined for biosignatures, the chemical fingerprints of life. We could search for cell structures, complex organic molecules arranged in biological patterns, and isotopic ratios that differ from non-biological counterparts. New maps of subsurface ice are fundamentally changing our exploration strategy. We are now targeting the water that remains, frozen in time. The third clue is perhaps the most tantalizing, pointing not just to past life, but to the possibility of present-day life. It comes from subtle and enigmatic features observed on the surface that hint at processes happening underground. Scientists have noted strange patterns, peculiar chemical compositions in certain soils, difficult to explain through geology and chemistry alone. Some of these features resemble structures created by colonies of microbes on Earth, which form biofilms and alter the minerals around them. While these are not proof, they are anomalies that demand investigation. They suggest the subsurface could be a potential haven for life. The Martian surface is incredibly hostile. It is bombarded by intense ultraviolet and cosmic radiation, experiences extreme temperature swings, and is almost completely devoid of liquid water. Below the ground, however, the story could be very different. Just a few feet of soil would provide excellent shielding from the harsh radiation. Geothermal heat and salts that depress the freezing point could create localized pockets of briny liquid water, even in today's cold climate. This idea of a deep, cold biosphere is a compelling one. Life, if it ever got a foothold on Mars, might have retreated underground as the planet's climate changed, persisting in a state of near hibernation, thriving in isolated habitable niches. This is why the search for signs of burrowing, microbial matting is so critical. Rovers like Perseverance analyze fine-scale chemistry, searching for organic molecules and other potential biosignatures. Every strange patch of soil, every unusual mineral deposit becomes a target for closer inspection. Orbiters can flag these locations from above. Rovers can then drive to them for in-situ analysis. The hypothesis is testable. If life exists underground, it must interact with its environment, consuming nutrients and expelling waste, leaving a detectable chemical signature, a subtle imbalance distinct from the surrounding geology. The search for life on Mars is not a single experiment with a simple yes or no answer. It is a complex, multifaceted investigation, much like a grand detective story. Each clue, the powerful winds, the buried ice, the hints of subsurface activity, is a piece of a much larger puzzle. None of these clues alone confirms the existence of life, but together they build a compelling case. They provide a strategic roadmap, guiding our robotic explorers toward the most promising locations where the mystery is the absence or presence of biology. Our tools and techniques are becoming more sophisticated with every mission. The interplay between these clues is what makes exploration so exciting. A prime future site might be a mid-latitude crater where wind erosion has exposed an ancient buried ice sheet. This synergy maximizes our chances, using one piece of knowledge to leverage another. We are learning to think like Martians, or like something that would need to survive there. This investigation is a global effort and uses a wide array of technology. Telescopes on Earth provide the big picture. Orbiters map minerals and weather. Landers are our hands. Rovers are our eyes. The Mars Sample Return Mission, a NASA-ESA joint effort, is the next step, bringing pristine Martian rock, soil, and potentially ice back to Earth. Extraordinary claims require extraordinary evidence. Scientists must be rigorously skeptical, ruling out non-biological explanations first. This painstaking work is the hallmark of good science and ensures discoveries the world can trust. So, what is the ultimate takeaway from these new Martian clues? The simple answer is that the search is more focused and more hopeful than ever before. Mars is not a simple dead rock. It is a dynamic world with ongoing processes that we are just beginning to understand. The stronger winds, the accessible ice, the hints of a habitable subsurface are not just interesting facts, they are actionable intelligence. They tell us that if life's traces are there, we now have a much better idea of where to find them. The search has moved from a broad, speculative phase to a targeted, scientific investigation. The question of life on Mars resonates far beyond the scientific community because its answer would be profoundly meaningful for all of humanity. To find that life arose independently on two adjacent planets would strongly imply that life is not a fluke, but a common outcome of planetary processes. It would suggest that the universe is teeming with biology and that we are likely not alone. Even if we ultimately find that Mars has always been barren, that discovery would also be significant, teaching us just how precious and rare the conditions that led to life on Earth truly are. The path forward is clear. Future missions will be designed with these new clues in mind. We will see landers equipped with drills capable of reaching the buried ice sheets. We will see rovers with more advanced chemical analyzers to sniff out the faint signatures of metabolism in the soil. And ultimately, we will see the return of Martian samples to Earth, where our most powerful instruments can search for definitive proof. Each mission is a calculated step, building on the knowledge of the last. International collaboration will be key, as the scale of this endeavor requires the best minds and resources from across the globe. In the end, the search for life on Mars is an expression of our innate human curiosity, the drive to explore, to understand, and to see what lies over the next horizon. The red planet continues to guard its secrets well, but it is also leaving us a trail of breadcrumbs. The winds are shifting, the ice is waiting, and the ground beneath our rovers may hold the biggest surprise of all. While we have not yet found life on Mars, we now know, with more certainty than ever, that we are finally looking in the right places. The quest continues with patience, with rigor, and with an enduring sense of wonder.